And, the first thing, and maybe we talked about this before, but there was a mathematician around the same time as Isaac Newton named Leibniz, and they developed calculus in parallel. Like, Newton was back in England, working alone in his study, developing the whole theory of calculus. And separately, elsewhere in Europe, can't remember what country, this guy Leibniz also independently developed calculus. And then after they started publishing papers, they realized that they were making the same discoveries. And so there was really two inventors of calculus. There was both Newton and Leibniz. Lagrange came a little bit later, really quickly understood calculus and also contributed to the theory of math. But whenever I say Leibniz notation, what we're talking about is this notation where I say, I want the derivative with respect to x of sine of x, for example. Or I could say something like y equals x squared. What is the derivative of y with respect to x? And the rationale behind this is that the derivative is kind of like the slope of a curve. If you zoom in really close to the curve at one point, to where it looks like a line, then what's the slope of the curve at that point? And since slope is rise over run, that's exactly the rationale behind writing dy over dx. To be a little bit more explicit, this lowercase d means a tiny change. And so whenever I write dy over dx, I'm talking about a tiny change in y divided by a tiny change in x. Does that fit your intuition with rise over run? Because y is the vertical direction on our xy plane, and x is the horizontal direction in our xy plane. And the reason why it's important that we talk about tiny changes in y over tiny changes in x is because we have to zoom into the curve really close before it looks like a line. And so this only makes sense if we talk about a tiny change in y divided by a tiny change in x. And that's the reason that we write the Leibniz notation the way that we write it. And then Lagrange notation is just more convenient because we like to define functions using function notation. And then when I want to denote the derivative, I can just write a little apostrophe, and that's easy. So it's like a shorthand. But that's what we call Lagrange notation. So I'll use both throughout the semester. We use both depending on what's going to be more convenient for us. The new material on your section 1.2 homework is this. We're going to now try to memorize the derivative rules that are called derivative additivity, derivative homogeneity. Try saying that 20 times fast. Homogeneity. Homogeneity. And then the derivative product rule and the derivative quotient rule. These are in your packet. But what derivative additivity means is this. Additivity. This means that if I'm taking the derivative of two functions added together, then this is the same as taking the derivative of f plus the derivative of g. And this is not so hard to remember. This is intuitively how you would hope that derivatives work, right? Like it's the least complicated way this could possibly work. If I had like something like this, then this is just 2x plus cosine. You just take the derivative separately. Hopefully that's how you expect it to work. That's what we mean by additivity. The next one of the rules is called homogeneity. And that's a really crazy sounding word, but this is maybe the simplest of all derivative rules, which is if I have some constant times a function, this is the same thing as if I can take the constant multiplier outside of the derivative. In other words, what if I'm trying to take the derivative of 7 cosine of x? That's the same thing as 7 times the derivative of cosine of x. And so that would be negative 7 sine of x. Okay? So anytime you have a constant multiplier, you can just imagine ignoring that when you take the derivative. Okay? So big complicated vocabulary word that means hopefully the simplest thing you can imagine. Just ignore constant multipliers when you take derivatives. So far so good? Okay, so this is where it starts to get a little bit interesting. This is the derivative product rule. And the derivative product rule tells me how to take a derivative of f times g, where f is a function of x and g is a function of x. And if I want to take the derivative of f times g, this is f prime g plus fg prime. Say it with me. F prime g plus fg prime. So, here's an example. If I have x times sine of x, I would say that x is the f part of this product, and sine of x is the g part, right? This looks like f times g. F prime is going to be the derivative of x. What's the derivative of x? 1. It's okay if you have to think about that for a minute. It's not something we've explicitly said. But x is the same thing as x to the 1 power. And now if I use my power rule, well, I would bring down, the power in front as a multiplier times x to the power 1 minus 1. So x to the power 0. What is x to the power 0? 1. So this is 1 times 1, which is 1. So this is not equals, sorry, that's after taking the derivative. But since x is the same thing as x to the 1 power, then when I take the derivative of x is 1. The derivative of x with respect to x. Hopefully this makes sense too. If I talk about a small change in x divided by a small change in x, I don't know. But this is the idea. So whenever I see this f prime here, I'm thinking about what's the derivative of x, and that would just be 1. When I see the g here, well, that's just sine of x. Plus f is x, right? What about g prime? That would be cosine. And so when I simplify everything, this derivative is sine of x plus x times cosine of x. In other words, the derivative of x times sine of x is sine of x plus x times cosine of x. That's an example of using the derivative product rule. And again, really quick, I'm going to check my work. No reason not to. This is what the function x times sine of x looks like. And the potential derivative that we found was sine of x plus x times cosine of x. And the way that I really want to check my work is saying this. Desmos knows how to take derivatives. I just have to type in y equals f prime of x now. And if I got the same answer that Desmos does, then I should have this black curve be perfectly overlaid on the purple curve. Okay? That's how I check my answer. That was a lot. Do y'all have questions? No questions. Y'all are either very smart or very shy. And that's the product rule. So product rule is where you find two functions where you're multiplying, like x times sine of x. And then you say, one of them is going to be labeled f, the other is going to be labeled g. And the rule when I go to write the derivative is f prime g plus fg prime. Okay, the last one is going to be called the quotient rule. And the quotient rule says if I take the derivative of f divided by g, so in other words, I'm dividing two functions of x, this is f prime g minus fg prime divided by g squared. So it looks pretty similar to the product rule, only we subtract instead of adding, and then we divide by g squared. So, as a quick little example, let's say I have the function sine of x divided by x. What would I say is f?
Sine of x.
Yeah, it has to be the numerator. And what is g? X. Is x. So f prime is cosine of x. G is
X.
x. F is sine of x. And then g prime is 1. Okay, and then what would g squared be?
Also 1.
The g squared in the denominator, I'm not taking a derivative. That's just the g function squared. So I have to write x squared. And I don't have to write times 1 if I don't want to. So this derivative of sine x divided by x is cosine of x times x minus sine of x divided by x squared. Does everybody see how we did that? Yeah. Okay. Let me put that in Desmos. And now our function that we're starting off with is sine of x over x. That's what it looks like. The derivative that we found is going to be x cosine of x minus sine of x. And then I want to divide everything, but not just that, but I want to divide everything, in these parentheses, by x squared. So that is the derivative that we found. And if I did everything correctly, then I can check it by making sure I got the same curve that Desmos gets when I use the f prime Lagrange notation here. No, that's right. That's how you check your work. Okay, questions about the quotient rule? Does that make sense? Yeah?
It's not about the quotient rule, it's about the homogeneity rule. Can you go over that one more time?
Oh, yeah. So what homogeneity means is if you have a constant multiplier. Notice the number 7, that's not a function of x, so I don't have to use the product rule. It's just a constant. 7 is always 7. So if I've got 7 times cosine of x, I don't have to worry about the 7. I just pretend it's not part of the derivative, and I only take the derivative of cosine. So homogeneity means you just ignore constant multipliers. They stay the same before and after the derivative.
And then you just make it negative.
That is negative because the derivative of cosine
negative
is
sign.
negative sign. Yeah.
Okay. So you only use the product rule when it's like e of x times whatever g would be, or something like that?
Yeah.
Okay.
You use the product rule when you've got two functions of x
Okay.
that you're multiplying. Now, I'm going to give you, I mean, we can work more examples together, but what I want to show you next, and I just want to make sure I get to this before we run out of class time, is this one. what I have here is g of x equals 5 times x times e to the power x times cosine of x. This is going to be one where we use the product rule. But the real tricky part here is that I don't just have 2 functions of x. I actually have 3 functions of x. I'm also going to be, just tacitly using homogeneity because I've got this constant multiplier 5. I don't have to worry about that. It's still going to be 5 at the end of taking the derivative. I just have to remember to rewrite the 5 later. But whenever I want to calculate the derivative here, I'm thinking about labeling these functions something like f, g, and h. And the derivative, when I'm done, is going to be like this. F prime g h plus f g prime h plus f g h prime. Okay, so every term in the product rule is going to have a factor representing each function. Only one of them will have the derivative. Only one of them gets the prime, and it changes. So f versus f prime, and then it's g prime, and then it's h prime. That's how I remember the product rule for multiple functions. So that means, what is f prime?
1.
1. What is g?
E of x
What is h?
cos x.
And notice I could have written times 1 for f prime, but you don't have to multiply that 1. And then f is
X.
g prime is
E of x.
e to the x. And then h is
Cosine.
cosine. And then lastly, f is
X.
x. G is
E of x.
e to the x. What is h prime?
Negative
Negative sign. Since it's a negative sign, I'll turn that positive into a negative and then parentheses. Notice I kept the 5. Constant multipliers, they just stay the same, beginning to end. If I was multiplying the whole thing times 5 to begin with, I multiply the whole thing times 5 at the end, because that's what derivative homogeneity is telling me to do. Now, I'm constantly terrified of making mistakes, so let's check my work. 5x e to the x cosine x. That is the function. That's the original function we're dealing with, right? And then what we found as the derivative was 5 times e to the power x cosine x plus x e to the x cosine x minus x e to the x sine x. That's the derivative we found together in purple. Okay? And then finally, to check my answer, I just make sure that me and Desmos got the same curve. And it looks like, yeah. It looks like me and Desmos got the same curve. So, answer checked. We did a good job. So, that's how you extend the product rule, if you need to have 3 functions multiplied together. But we can keep doing more examples together.
So can the product rule just go on and on and on and on, like 3, 4, 5, 6, 7 functions?
Yeah.
Please don't ever make us do that.
Yeah.
It's really unfortunate.
Yeah.
Okay, let's do some examples together. What's this derivative right here? I think we maybe did this together a second ago. 2x plus
Just cosine.
cosine of x. Great. You just take the derivative separately. What's this derivative right here?
You can't square
C
that.
squared x squared.
And maybe 2. That would be negative.
So bring down the negative 2 and becomes plus 2x to the negative 3, right?
Yeah.
Yes.
And then this is secant squared x plus 2 over x to the third, if you want to write it fancy. Okay, but yeah, the idea is you take the derivatives separately. Anytime you're adding or subtracting, you just take separate derivatives and it's fine. If this is 3 cosine x, what's the derivative?
Negative 3 sine x.
Negative.
Negative 3 sine x. So the 3 goes along for the ride. If this is negative arctangent of x, what's the derivative?
Negative 1 over x squared plus 1.
Perfect. Yeah, the negative just goes along for the ride. It's negative 1 over x squared plus 1. Because the negative is a constant multiplier. It's like a negative 1 constant multiplier. Product rule. What is this derivative? X squared times cosine of x.
Alright, I'm gonna get scratch paper.
2x cosine x.
Yeah, 2x cosine of x minus x squared.
Oh, yeah.
Right. The product rule is f prime g plus fg prime. So you've got to decide what is my f, what is my g, and then you can find what is f prime, what is g prime, and then you just put it together according to the formula. So f prime g would be 2x cosine of x. And then fg prime would be x squared negative sine of x. And since it's negative, I'll make that plus sign into a minus sign. And that's my derivative. Questions? No? All good? All right. We already did sine of x over x. What about this one? What about this one? If I've got 1 over cosine of x,
So
I know I'm dividing, so I should use my quotient rule. And my quotient rule says the derivative of f divided by g is what?
F prime g minus fg prime over g squared.
Very good. So you guys have already memorized it. Awesome. F is going to be 1. G is going to be
Cosine x.
cosine of x. What is f prime?
What is the derivative
No.
of 1?
This is a great question.
To the of 0?
Yeah,
to the 0.
Hudson's right. That's a 0. That's my derivative of 0. So I'll give you the kind of dumb definition, or I mean the dumb reasoning, if you will. 1 is the same thing as 1 times x to the 0.
Mm-hmm.
Bring down the 0, and this is 0 times 1 times x to the negative 1, but you're multiplying by 0, so this is 0. A reason that I think makes more sense is like, what if my function is 1? Ooh, something is not right about this website. What if my function is just the number 1, right? That's my code. The derivative is the slope. of this curve. What's the slope of this curve?
0.
Everywhere, the curve is perfectly flat, so the slope must be 0, so the derivative is 0. Okay, so anytime I have any constant, it could be the number 2, it could be the number 3, it could be the number -1/2, right? Any constant is always going to have a derivative of 0. Okay, so whenever I have a constant like the number 1, I take the derivative and it is 0. What is the derivative of cosine?
Negative sign.
Negative sign. So putting it all together with my formula here, this derivative of 1 over cosine of x is going to be f prime g, which is 0 times cosine of x.
So it's just 0.
I'm not going to write it because, yeah, 0 times anything is 0. Minus f times g prime. Of course, f is 1, so this is really just minus g prime.
So it's
Minus g prime is minus negative sine of x divided by g squared, and so that's negative sine of x squared. No, I lied. What mistake did I make? Cosine of x squared, yeah. And this is positive sine of x divided by cosine squared x. By the way, who is smart enough to tell me? Who wants $5 bucks? All Bluey fans in the room.
Isn't that
What is 1 over cosine?
secant?
Secant. Okay. And if you've memorized this, what is the derivative of secant?
Secant x times tangent x.
Yeah, secant times tangent. So how come over here I got secant x times tangent x, but over here I got sine x divided by cosine squared of x?
Well, sine over cosine is tangent, and secant is 1 over cosine, so it's the same as that times that.
Yeah. So this is tangent x, and this is secant x.
Just math. Just math.
Wow.
So multiple different ways to write trig functions.